Let's take a look at the other part of section 6.3, which is the best approximation theorem. What does the best approximation theorem tell us? Well, it tells us that W is a subspace of Rn, and Y is an element, which is a vector in Rn, and that Y hat is the projection of Y onto W. Then Y hat is the closest point to W in Y. So here's what all of this means. I have a set W, and obviously I'm looking at R2 right now because I'm looking at a picture so that I can try to visualize what exactly is happening. So I have this subspace W of R2. Then I have Y, which is some vector that's not in W, but it is in R2. I know that I can create a projection, and remember that projection is just if I drew a right angle down, that this guy right here would be my projection vector. This is my Y hat. So that's what we've been working on, is finding that projection vector. And then we've also been obviously working on finding this little guy as well. But what this tells us is that Y hat is the closest or the best vector in W to use to approximate Y. And essentially then what we're saying is this is saying the distance between Y and Y hat is going to be less than or equal to the distance between Y and any other vector in W. So let's take a look at what we mean by that. Let's say I have some vector all the way out here. I can see that the distance between Y and that vector is greater than the distance previously found between Y and Y hat. I can do the same thing with one that is shorter, say this guy right here. So now I have another vector that's in W because it's on that line, and if I were to find the distance between that vector and Y, then obviously it's greater than what I'd found previously. So essentially what we're saying is the process that we were going through to find that projection is the closest point in W to Y. So it is the best approximation in W. So I want to do an example with you where we can go through all of the steps and not only do the math and find the solution, but actually kind of see what exactly is happening. So that's why I've chosen a very simple example here. We have W as the span of 2, 1. So looking at my picture, I've already drawn in 2, 1, which is right here. And we'll just call that vector U, just so we have something to refer back to. So this little guy is vector U, and W is the entire line created by all of the multiples of U. So that's span of U. I'm looking for the best approximation to Y, which Y is 3, 4, and I want that obviously to be in W. So what I'm looking for is if I were to draw a perpendicular line, my theorem says that that is going to be the best approximation to Y in W. So when I say that is going to be the best approximation, I'm referring to this vector. The vector created by, and we call that Y hat if you recall, the vector created by that perpendicular line from Y to our span, essentially to our line, and that's what I'm looking for is Y hat. So how do I find Y hat? Remember, Y hat is just the projection of Y onto W in this case. And to find it, we're just using that formula that says we're going to take the product of the dot product of U and Y over the product of u and u, and then multiplied by u. So this is that same formula we've been using. So here we have y hat is equal to 2 times 3, which is 6, plus 4 times 1, which is 4, over 2 times 2, which is 4, plus 1 times 1, which is 1, multiplied by u. And again, that gives me 10 over 5, multiplied by 2, 1. That gives me 2, multiplied by 2, 1. That gives me 4, 2. So does this make sense? Well, if I look back over here to my picture, 1, 2, 3, 4, 1, 2 appears to be this point right here, and that makes me feel all warm and fuzzy inside, because that's sort of what I drew in anyway when I drew that perpendicular line, so it would make sense that that is 4, 2. Then the question might become, well, how good of an approximation is it? According to my theorem, it's the best approximation, but what exactly does that mean? How big is our error? So to find the error, all I'm going to do is I'm going to find the magnitude or distance between y and y hat, which means I'm going to take y, which was 3, 4. I'm going to subtract y hat, which I just found to be 4, 2. And then I'm just going to find that distance. So I'm finding the distance 3 minus 4 is negative 1, 4 minus 2 is 2. And if you'll recall, how we found the distance is we just took the dot product of that vector by itself. So the square root of negative 1 squared plus 2 squared, which means 1 plus 4, which means my error is radical 5. So that is the distance, which is the error, which is the magnitude. You might see it referred to as any of those things. Here's a question for you to try on your own. So I would like you to follow the same process to find the closest point to y in the subspace spanned by v1, v2. When you are ready, press play to see how you did. So again, we know that the closest point to y in the subspace is found simply by the orthogonal projection, which means all we have to do is find y hat. And y hat can be found, in this case we have two vectors, so I'm going to take y times, the dot product of y and v1 over the dot product of v1 with itself, multiplied by v1. Forgive my lack of arrows. And then I'm going to add to that the dot product of y v2 over v2 v2 dot product multiplied by the product, multiplied by vector v2. So in this case, that is going to be 3 times 3. I'm going to go to the next line because we're going to have a lot of work. So y and v1 gives me 3 times 3, which is 9, plus 1 times 1, which is 1, plus negative 1 times 5, which is negative 5, plus 1 times 1, which is 1, over the dot product of v1 with itself. So that's 3 times 3, plus 1 times 1, plus 1 times 1, plus 1 times 1. And all of that is going to be multiplied by 3, 1, negative 1, 1. For the other part of this, I'm going to take v2 times y, so the dot product, 1 times 3, which is 3, plus negative 1 times 1, which is negative 1, 1 times 5, which is 5, negative 1 times 1, which is negative 1. The denominator is the dot product of v2 with itself, so 1 times 1, plus negative 1 times negative 1, plus 1 times 1, plus negative 1 times negative 1. All of that times v2, which is 1, negative 1, 1, negative 1. So now let's do a little bit of math. I get 9 plus 1 is 10, plus negative 5 is 5, plus 1 is 6, over 12, so that's 1/2. So 1/2 of 3, 1, negative 1, 1. I'm adding to that 3 plus negative 1, which is 2, plus 5 is 7, plus negative 1 is 6, 6 over 4, which reduces to 3 halves, times 1, negative 1, 1, negative 1. So if I continue that, I'm going to end up with, let's see, 3 halves, 1 half, negative 1 half, 1 half, and the sum of that and 3 halves, negative 3 halves, 3 halves, negative 3 halves. And if I add correctly, I end up with 3 halves plus 3 halves, which is 3. 1 half plus negative 3 halves, which is negative 1. Negative 1 half plus 3 halves, which is positive 1. And 1 half plus negative 3 halves, which is negative 1. So the closest point to y in the subspace is this point, 3, negative 1, 1, negative 1.